Large language models generate text, code, and images based on user prompts. This is generative AI. Agentic AI takes those same models and gives them autonomy, enabling stateful, proactive execution where the AI operates independently to achieve a specific goal. Instead of waiting for human commands, an agentic system runs on a continuous operating loop. It perceives its environment, formulates a multi-step plan, selects external tools to execute that plan, commits the results to memory, and uses feedback to correct its own errors. This diagram shows the structural difference. On the left, the standard user prompt flow is strictly linear. Input goes in, text comes out. On the right, the autonomous workflow is an iterative loop. A central orchestrator routes the user's goal to a planner, which triggers real-world API executions, stores the state, and cycles until the objective is complete. By April 2026, organizations deploying these multi-step agent architectures at production scale achieved a median return on investment of 171%, successfully completing complex workflows like automated code deployment and end-to-end customer service resolution. The underlying language models already possess the necessary reasoning capabilities. The bottleneck for enterprise automation is no longer raw intelligence. It is the orchestration, routing, and governance of that intelligence. Despite the obvious financial upside, the current enterprise AI landscape is defined by a massive gap between experimentation and operational reality. Almost every major company runs internal agent pilots, but very few scale them into daily operations. This data funnel shows the attrition rate. 97% of enterprises launch agentic AI experiments, but sustained production plummets to 12 to 25%. That leaves an 88% failure rate, a dead zone known as pilot purgatory. Research shows these failures cluster around specific bottlenecks: fragmented corporate data, lack of enforceable security policies, and brittle single framework pipelines. Standalone scripts simply cannot manage the multi-step reasoning required for production-scale resilience. Organizations that bridge the gap from pilot to production do so by treating orchestration as an infrastructure problem. By implementing an application layer operating system, they provide the native routing and identity management necessary to resolve the technical gaps crashing isolated agentic experiments. An operating system abstracts the complexity of the underlying models. It provides the native execution, scheduling, and governance required to transform fragile scripts into resilient, enterprise-grade AI workforces. Qualisar OS serves as a blueprint for this universal orchestration layer. It is an application layer operating system purpose-built to manage heterogeneous, multi-agent systems, regardless of the specific framework they were written in. This block diagram maps the complete six-layer architecture of the operating system, bridging transport interfaces, core orchestration, and deep infrastructure persistence. Looking at the center of the system, we find the core orchestration pipeline. Every task begins here, passing first through a module called Forge. Forge is an LLM-driven team design engine. It translates a user's high-level goal into a complete workforce architecture, dynamically engineering a team of specialized agents with specific roles, tools, and topologies for that exact task. By querying historical reinforcement learning data, Forge determines how many agents are needed, assigns specific roles, attaches necessary API tools to each individual agent, and defines the communication pathways between them. An agentic operating system goes beyond executing predefined instructions. It autonomously builds the optimal corporate structure required to solve the problem it was handed. Simple agent frameworks rely heavily on sequential chains, where Agent A finishes its work and passes the output to Agent B. If Agent A makes a logic error, that hallucination cascades through the rest of the chain, creating a single point of failure. To prevent cascading errors, Qualisar implements 12 distinct multi-agent execution topologies. One of the most robust is the grid topology. This visualization shows the grid pattern. Agents are arranged in a two-dimensional matrix, communicating exclusively with their 4 adjacent neighbors. It functions like a cellular automaton applied to LLM reasoning. The system iteratively refines the output, converging only when the collective logic across all nodes stabilizes. For high-risk outputs requiring democratic quality control, the system deploys the maker topology. A single proposer agent generates solutions, while multiple voter agents evaluate the work. The proposal loops through continuous revisions until a strict 66% approval majority is achieved. These execution patterns physically constrain the pathways of the AI's logic. Hallucinations and errors are trapped, debated, and corrected by network consensus long before the final output reaches the user. Running a complex multi-agent network exclusively on a frontier model like GPT-4 is a massive financial drain. Hard-coding a single provider guarantees an organization will overpay for simple sorting tasks and hit strict rate limits during high-volume operations. Moving down to the routing layer of the Qualixer block diagram, we see how the OS handles compute allocation dynamically. The system maintains a live runtime catalog of models across 10 different providers, feeding availability and pricing data into a 3-layer routing architecture. This top layer runs an epsilon-greedy contextual bandit. Based on the current budget and task type, this meta layer learns over time whether to prioritize cost, quality, or a balanced approach for a given step. At the base layer, the OS runs a partially observable Markov decision process, or POMDEP. Because model quality fluctuates, it continuously updates a belief distribution based on incoming signals to guess which model will perform best under uncertainty. True operating system routing treats artificial intelligence as a dynamic, fungible commodity. Enterprises automatically provision cheap, fast models for basic subtasks, reserving high-cost frontier reasoning exclusively for the most demanding cognitive work. As these agentic systems self-evaluate, they encounter Goodhart's law. When a measure becomes a target, it ceases to be a good measure. If an agent's goal is to get its work approved by a specific evaluator, it will eventually learn to exploit the quirks of that judge. The agent will produce fabricated outputs that score perfectly on the internal rubrics, but are completely useless in reality. Looking at the far right of the Qualixer architecture, the quality assurance pipeline is built to stop exactly this kind of metric gaming. This graph tracks the Goodhart detection module. It monitors cross-model entropy. If the score inflation of an agent rises while its entropy metric drops below 0.3, the OS detects that the agent is manipulating its specific judge. The evaluation is immediately thrown out, and a fresh judge panel is rotated in. To prevent the judge models themselves from losing accuracy over thousands of evaluations, the system relies on a mathematical firewall called the JSD drift monitor. This equation calculates Jensen-Shannon divergence, comparing a judge's current scoring distribution against its original baseline. If the divergence crosses a hard-coded threshold of 0.877, the drifting judge is automatically suspended and recalibrated. Without rigid, hard-coded mathematical firewalls, continuous self-improvement is impossible. Any autonomous system will inevitably collapse into a feedback loop of fabricated metric optimization. Computer scientists recognize a theoretical impossibility result known as the self-evolution trilemma. It proves that a system cannot simultaneously achieve strong optimization, perfect value capture, and robust generalization. A perfectly aligned, infinitely self-improving AI is mathematically impossible. A functional operating system navigates this trilemma by implementing strict escape hatches. Rather than attempting unbounded improvement, it enforces deterministic limits, like hard-capping redesign loops at exactly 5 iterations, before halting execution and forcing human escalation. These internal technical boundaries map directly to external, real-world regulatory pressures. Global compliance frameworks like the EU AI Act, the NIST KC Initiative, and ISO 42001 now mandate this exact level of architectural transparency, risk management, and bounded autonomy for enterprise deployments. The dense statistics running inside the agentic operating system, the entropy monitors and drift bounds, are the literal mechanisms that satisfy the legal requirements of global AI legislation. Enterprise architects are moving past simple prompt engineering. The scale of the technology demands a shift toward rigorous, governed pipelines that monitor and constrain intelligence. Enterprise intelligence now depends on the same architectural rigor applied to any other mission-critical stack. It requires governed routing, robust multi-agent topologies, and mathematical bounds on drift. The path to production scale requires moving beyond isolated prompts and into these resilient, orchestrated pipelines.